Thanks for coming to our 3D printing coffee break. My name is Brandon Brown. I'm an additive manufacturing application engineer here at Quest Integration. Before we get too in depth, a little bit about me. I have a bachelor's of science in mechanical engineering from Montana State University. I graduated in 2017. I have over 20 certifications with Formlabs, Markforged, and SolidWorks. I've been a Quest employee for over 4 years, almost 5 now, and I'm an avid mountain biker and skier outside of work. So in this series, we've been talking about 3D printing, namely in the professional environment, and what it looks like to adopt additive manufacturing, whether or not they're professional production tools, et cetera. Like last time, we talked about what makes a good professional 3D printer. This time, we're going to talk about proving a return on investment for 3D printing to see if this is something that would make sense for your company. So, in order to discuss this, we're going to talk about a few things pertaining to this issue, namely how to select parts for additive manufacturing, what parts make sense for additive manufacturing, how you would typically cost 3D printed parts and some of the associated cost factors, proving return on investment. So some of the things that you'd have to calculate to see what your return on investment would look like and what it would look like to get a return out of investment in additive. And then we're going to go through an example of sorts that would actually a real world example that would it's going to kind of illustrate how this works. So first of all, let's talk about how to select parts for additive manufacturing. And this isn't so much more of a technical discussion as it is an economic discussion. So additive manufacturing part cost is fixed or constant, regardless of complexity or part volume. So no matter what, it is always going to cost the same to manufacture a part regardless of volume. This might change a little bit with some methods. It might have a slight slope to it, but it is relatively constant. However, with traditional techniques, this contrasts with additive, you typically see quite a variation of this. It's typically much more expensive to make less parts than it is to make more parts. This is because there's typically more setup associated with traditional processes and more investment associated up front to make a part than there would be. And additionally, additive manufacturing stays constant with complexity, and traditional manufacturing methods typically increase in cost with complexity. So this is another really interesting dimension. Because of this, we want to make sure that we are keeping the parts we're producing additively in kind of the areas additive makes sense in. So this is typically where it's most cost effective, which is either with low volume parts or with parts that are very, very complicated and difficult to manufacture with other methods. Outside of this, there might be other tangible benefits depending on your goals here, but it typically would make sense to look at a more traditional process for, say, really high volume production or really low complexity stuff, depending on what you're doing. But there could be cases made for additive as well, as we'll talk about a little later. There's some non-tangible benefits there, depending on what you're looking at doing. I included this chart because I think it illustrates it pretty well. These are a few common production technologies. 3D printing, again, really fits kind of more in the lower quantity, high complexity area. This is starting to change and morph a little bit, but typically outside of this, some other processes might work a little better. This just kind of illustrates the previous, kind of add some context to the previous point. So how would you select parts for AM? What should you look for in parts that you're going to additively manufacture outside of, being kind of more complicated or lower volume? So again, lower production volumes, complex parts are great, but really you want to also try and look for parts that can be simplified or consolidated. Basically, they can be modified to leverage the advantages of additive manufacturing. So consolidating assemblies into single parts to save on labor and assembly costs and QC issues down the line. You also want to look for parts that match AM process capabilities and materials. It can meet all these other criteria, but it could just be impractical to do with AM or even impossible with where the technology's at currently. So you want to make sure it actually matches the capabilities and materials that you need for your application. Also, one of the main things, one of the places I like to start kind of start in a discussion about this is looking for problem parts. So when you're looking for problem parts per se, you're typically looking for parts that are difficult to make, that have long lead times or unpredictable demand. These are the parts that make your engineers and your production staff just kind of groan, and they complain about these parts. Um, I've seen quite a few of these in case studies or even working with some clients. Typically, these are parts that are great for additive, depending on your industry or your application. So this is always where I like to start. And depending on whether or not it's depending on the application, again, sometimes you can look at these parts and even though it might not seem super practical at first, there are ways to make additive work for these, and it solves a lot of problems all at once. Once you have chosen parts for additive manufacturing, it's also really important to optimize them. So this might make or break the use case in some cases, because design for additive manufacturing, or DFAM, brings out the true potential in 3D printing. Just like anything, if you're trying to make a part that isn't suited or designed for a process, it's not going to work as well. But this is especially true for additive, because while you do have a lot of design freedom, they do have a capability to produce very complicated, complex parts, 3D printers do, they still have design constraints, and you still need to abide by these to really bring out the true potential of 3D printing in your organization. If you do this, though, you can definitely start reaping some of the rewards. So let's talk a little bit about costing 3D printed parts. Once you have a couple that you think might work, you've optimized them for additive manufacturing. It's probably time to start looking at how much it would cost to do it with additive. So first, you want to look at some of the cost factors and incorporate these into your calculations. The first one, and probably the biggest one for most users, is material use. This can be obtained through slicing software most of the time. This is a great example of our Eiger software right here. It actually will tell you the material cost right off the bat for your part. But a lot of slicing softwares will simply give you the material volume used. This can be calculated from material usage and bulk cost. So I'll use our Formlabs printers, for example. They'll give you the volume of the resin you'll use in your print. All you really need to do is calculate the price per volume of the material you're using. In this case, it would be gray resin, which is $149 per 1,000 milliliters, which is 14.9 cents per milliliter, and you simply multiply this by the amount of material used for your part or your print job, depending on what you're costing. You can also calculate this from the length of filament used if your slicer doesn't really support this. I know some don't support that, but that's pretty easy. You just calculate the volume of filament used with the length of filament used. A lot will give you that as well. But that's kind of the first step into getting these cost factors, is getting the material use. Speaking of material use, that we're not actually done with this discussion, because with some methods and printers, there are other costs that may need to be calculated and added accordingly. So like one-time consumables or post or pre-processing steps. A great example of this is our Metal-X system. So there are 3 steps to this process. You print the part, which actually in this case, there's a one-time consumable there. It's a print sheet. This is used once a print. And then, you wash and you sinter the part. The sintering step requires sintering gases, which are certainly not free. So you definitely have to account for that as well. And you can just divide these into the number of parts you're doing to get to spread this across the cost per part in your calculation. If it's significant, you can also add or divide shipping costs into the material costs or anything else you're doing. I know I do this for our sintering gases. This works really well for regular orders of specified quantities. Like say you're gonna be printing lots, so you're ordering filament every say quarter. You're ordering a pallet of like say 50 spools. You can divide that into your material costs as well for your calculations to get an even more accurate return on investment or costing calculation. Other factors, electricity cost is a big one. For some methods, you can either measure this if you have a printer, if you want to get really into it, or assume peak draw, which is what I do. So I just assume my printers, especially the small ones like our composite Markforged printers, our Formlabs printers, and our Cindo printers, and just kind of use that as a baseline, just assuming peak draw, because they don't draw much. I think it's like 1.5 amps for some of those printers. And then I also look at the consumables cost. So every printer has a consumable, and a lot of these printers have service lives on their consumables. I just like to incorporate the cost of the wear components. So like for our Markforged printers, those are our Bowden tubes and nozzles. And then for our Formlabs printers, for example, we have resin tanks, which are actually given in liters of resin printed. So you can actually back out the cost, like say per liter of resin printed or milliliter of resin printed or hour of print time, and add that into your machine cost. Another cost to consider is labor. So this is any post-processing, loading, or unloading labor. Depending on the machine, this could be insignificant or very minimal, like not even worth calculating minimal, or it could be, say, you're post-machining metal parts and you're using some methods that require that as a step in the process. This could be significant. So a lot of times you won't need to incorporate this, but depending on the process or your workflow or your application, this could be necessary. So what does the calculation for a 3D printed part cost look like? So typically, I like to start again by calculating the machine rate. So the electrical cost per hour plus the consumables cost per hour. So just adding those two together to get a rate of operation for the machine. And you could even add labor into this if you knew it took a certain amount of time to set up and unload the machine or load and unload the machine. You could add that to this as well. Then you just simply calculate the part cost, which I typically do it by multiplying the print time by the machine rate of the part. I just typically round to the nearest hour, round up for a more conservative estimate, and then add the material cost, the raw material cost, and then I add the consumables cost in the sense of like one-time print or one-time operation consumables, plus the labor divided by the parts in the build to get a per part rate, an equally distributed per part rate of those costs. So now that we have our kind of machine calculations covered and some of the costing calculations covered, it's good to we can now start looking at proving an ROI and calculating some of the return on investment related parameters. So the first thing I like to do with this is compare the cost versus the current or other processes. Depending on your application and what you do going to do with the 3D printer, like if you're just going to be making a lot of random stuff like prototyping different products, you're not going to be doing, say, series production. Looking at a couple different applications and a couple different parts that you print somewhat regularly or parts that are representative, this might be good enough to justify the 3D printer. You might just be like, wow, this is a lot cheaper than what we're doing now. We could use this right away. But if you're looking at more of a manufacturing application, whether you're building tools around the shop or even end use parts, it's really good to calculate the other parameters. So the first one we're going to do is calculate the break even point, which is simply just the volume of parts we'd have to make for a given part to break even on our investment. So that's just all we need to do is calculate our savings per part, which is just the cost, the traditional cost, or another cost that we're comparing it against, minus the 3D printed cost that we calculated previously. And the break-even volume is simply just the machine cost or investment divided by the savings. Then we can calculate our return on investment parameters. We can calculate our investment gain by multiplying the production volume by the savings, the planned production volume that is. If you don't have a planned production volume, you can just simply do some hypothetical math here and say, if we're going to make this much, we'd gain this much. Then we can calculate our return on investment, which is our investment gain minus our investment cost divided by our investment cost times 100. This is just a percentage that percentage of the original investment that we would gain. And then one that's really important too is time to break even. So this is kind of a guessy number, but you can calculate it and get a rough idea. Say if you're doing serial production, that would be the break even volume that we calculated times the print time. Even if you gave it, say, a few weeks, few days, or even a month plus or minus, should give you a rough idea of when you could expect to get your investment back. Another important thing that it's important to do when looking at a return on investment in 3D printing, it's important to look at some of the kind of non-tangible or like non-quantitative benefits that may show up in cost savings. Your cost savings calculation is indirectly by just being cheaper than the other processes in some way, but it's just really important to consider, especially from like an organizational perspective. So things like reduced labor costs, faster time to market or user, being able to get parts to the people that need them faster without all the hassle. Supply chain benefits like being able to maintain a digital inventory, not having to tie up a bunch of capital and keeping part inventories and just keeping them printing what you need kind of when or where you need it. Having reduced downtime, being able to say keep custom equipment up and running without having to, again, it kind of ties into the faster time to market, time to user, being able to get the parts people need to them faster. IP protection is another one that people don't really talk about much, but with 3D printing, especially doing it in-house, you don't have to have that IP change hands several times. You don't have to send it to an external vendor. It's kind of just stays right there in your hands. Additionally, and this kind of ties into a few of the other ones too, it gives you flexibility. So in addition to saving time and money kind of across the board for your processes and for your organization, it gives you an additional capability that's very, very flexible. Like say you're doing serial production of a part, but you need to print something suddenly on the next job. There's no retooling required at all. You simply just change the file you're using and hit print, and you get what you need. It adds a lot of flexibility to your organization, especially if you have an industrial additive manufacturing system. So now that we've covered some of the return on investment parameters and some of the things you want to look for and calculate when trying to determine your return on investment, let's go ahead and do an example. So these grippers right here, those black grippers on that robot arm, are made by a company called Dixon Valve. They're heavy 3D printing users of all kinds. They make oil and gas couplings for they make like piping oil and gas couplings for that industry. And they do a lot of this kind of stuff. They're very into automation. So they were originally paying, this is just for this one specific gripper, but $285.61 to machine each of these grippers. They're able to print these for a material cost of $9.45, and it takes them about 8 hours a gripper to print. So even though the actual just blank cost comparison here looks pretty good, let's go ahead and take a look at what it would actually look like to get their investment back, what their ROI calculations look like. So we'll assume they're using a Mark Forged X7 here because it's a factory floor. They're pretty high volume users. It seems like a good fit for them. The first thing I'm going to do is calculate the machine rate for this machine. We're going to assume Dixon Valve, just for the sake of this example, is in Post Falls, Idaho, where I've calculated the electrical use of the machine to be about $0.01 an hour with its current rates, assuming peak draw. And then I'm going to add in the consumable cost per hour. And this is slightly overestimated because I'm considering all consumables here, just to make sure our machines are well maintained and they're not going down. So we get about 32 cents an hour for our machine rate. Then if we look at our part cost, which we can factor this into our part cost now, simply just 8 hours of print time per part times 32 cents an hour for machine rate plus $9.45 in raw material, and we get $12.01 per part. Now we can calculate our savings. So per part, that means we're going to be saving about $273.60. And this is a pretty extreme application. It is actually a real thing. This did happen to Dixon Valve. They did save a lot of money. I think it was like $36,000 on this project alone or something. And then the break-even volume we can calculate, which in X7 is about $76,000 all in with the support plan, with an installation, and the printer itself just kind of fully loaded. Divide our savings into that, and we get about 278 parts. In this case, we need to break even. Then we're not going to actually calculate these because, again, I don't have the production volumes for these, but we will plot them here in a second. Our investment gain is just simply our production volume times our 273.60, which is our savings. And then our ROI is just our investment gain minus the cost of the printer divided the cost of the printer times 100. Our time to break even, however, we can estimate. So again, 278 parts times about 8 hours each, which puts it roughly at 93 days or roughly 3 months. If we say add a month to that, we still have about a 4-month time to ROI printing stuff like this. When we plot our investment gain, which I actually have the net gain here, which is just subtracting the cost of the printer from the investment gain, and the return on investment as a percentage here, we can see that our break-even points are right here at 278 parts. And that gives us a kind of a rough idea of when we will get to our return on investment. But then we can kind of use this chart too to look further into the future to see as we increase our production volumes or make parts like this, if we assumed all the end effectors cost like this, how much money we would save in the future versus traditional processes. Something I wanted to talk about too is a lot of times one part might not get a return on investment. It might be like a partial return on investment. You might have several parts. That's why it's important to look at several different applications and parts in your organization that might fit well with additive to see if you could save money with them, because you can do this calculation for each of them. And if you know how much you're going to make of each, you can kind of concatenate them together to get like a total ROI chart, or like a total, like we're going to save this much on this project, this much on a next project, and add these all together to build a case for additive manufacturing in your organization. And then additionally, if you look at the other kind of non-tangible benefits we discussed, the organizational benefits of additive manufacturing, some of the stuff we've talked about in this webinar series, you can use that as well to kind of push and make a case for additive, for switching to additive, or at least starting to adopt it and explore it in your organization. If you're interested in learning more about 3D printing, we actually now offer training if you're interested in that. And if you want to learn more about our printers and how they can fit into your organization, or just curious about kind of what we do here, our printers, and want to start looking at this yourself, you're definitely more than welcome to reach out to us. I'd love to talk to you about this at that phone number or that email address. Thanks for attending, and don't miss our final session on June 16th, which is how to properly implement 3D printing in your organization, and kind of what that might look like in different phases. I'm going to open it up for questions now, but that's all I have for you guys today. Thank you for coming.